AI Never Sleeps. I'm Ash Bennington, joined as always by Mikhail Voloshin. Mikhail, welcome back.
And we got a special guest today, Phoenix, who's a special guest every day. But today we're talking about quantum mechanics, which means she's going into a box.
Oh man, that's the world's worst joke. It's a good way to open because it'll literally just be all downhill from here. Mikhail, you called me up earlier today, very excited to talk about something that had been happening, a breakthrough in quantum computing.
Google just changed the world with Willow. Imagine solving a math problem that would take the world's fastest supercomputer 10 septillion years. But Google suggests Willow can do it in 5 minutes.
Google announced the first verifiable quantum advantage on their quantum computer chip Willow. This breakthrough will change everything.
Google's quantum AI founder, quantum computation occurs in many parallel universes in line with the idea that we live in a multiverse.
Didn't understand it then, still don't understand it now, but I want to talk a little bit about this because this is something that, in your view, may be important.
It's something that's getting a lot of attention. It's something that a lot of folks have been chatting about on various news networks and channels and whatnot. It is the announcement by Google that their Willow quantum processor has achieved something called quantum supremacy. What this means for everything from AI to crypto to just computing as we know it, the way that the future of banking will work. There's also a lot of misinformation out there, and I just figured that we better get on this.
Let's do something real quick. Let's just zoom the camera back a little bit before we get into this specific news flow, this idea of verified quantum advantage. You're going to explain what that means. Let's talk a little bit about quantum computing. Here's basically what I know about quantum computing, which you could essentially fit inside a nutshell. Quantum computing is something that's always about 2 years away, and it's always going to change humanity's grasp of technology. It's always pushed as something that is going to be a huge breakthrough when it gets to scale, when it gets to be practical to do at commercial levels. But there are a lot of limitations behind it. It has to be kept like near absolute zero. I mean, there's all these things that we always hear about quantum computing, but nonetheless, still a very impressive technology. This is about doing computing based on quantum physics, the subatomic particle level of physics. Explain a little bit about what it is, how it works, and why it's so important.
So quantum computing leverages a specific property of quantum mechanics, which is something called superposition. The idea is that when you're not looking at a particle, it is in all possible states at the same time, or at least according to certain interpretations. This is a little bit like if I were to flip a coin and it lands, but I haven't yet observed whether it's heads or tails, then it is both heads and tails until I take off my hand and look at it.
Hence your joke about Dr. Schrödinger and putting the cat in the box, who's now aggressively licking its paws.
So Dr. Schrödinger formulated his famous Schrödinger's cat experiment to ridicule the concept of superposition. So a lot of people don't seem to understand. This is one of the many, many misconceptions that I want to clear up. Ash, presumably you've heard of the Schrödinger cat experiment, right?
I have.
For our listeners out there, I hope you all know, as far as any reputable scientist knows, nobody has ever actually performed the Schrödinger cat experiment. But the idea is that if you put a cat in a box, you seal that box with a vial of poison that is hooked to a hammer that gets tripped by a Geiger counter, and it's measuring the decay of some piece of radioactive matter. Once it hits a certain number of clicks, it'll release the poison and the cat will die. The Schrödinger experiment basically says that as long as the box is closed, the cat is in a superposition of states of simultaneously being both alive and dead. Now, this eponymous experiment of Schrödinger's has gotten really, really famous because of its ridiculousness. Schrödinger was arguing originally against some of his colleagues that were basically saying it is how microscopic objects work. And he goes, okay, smartasses, I'm going to devise a system where a macroscopic object is actually based on the outcome of a microscopic one. So your little delineation about how the nano world works is no longer valid. You can't say that like different physics apply to one world or the other.
And
so,
by experiment, we mean thought experiment, to be clear.
Yes. A hypothetical, they called it a Gedankenspiel, a thought game. So it's really ironic that the thing that Schrödinger is remembered for in pop science the most is a joke that he was trying to make about how physics doesn't work.
Okay, let's bring us to qubits here, the fundamental unit of quantum computing, and how they are and are not analogous to bits in classical computing.
So this is really where you get down to why quantum computing is so promising, at least on paper. A bit in classical computers is always a 1 or a 0. That's how we defined it. And that goes all the way back to Claude Shannon's seminal paper where he invented the process of doing binary math with electronics. If you're trying to solve a complicated computational problem, if you want to do it through a conventional computer, you can describe that problem through a certain number of bits, and you can iterate through all possible combinations of those bits. The problem is you can only evaluate any one combination at a time. So even a very, very fast computer would have to work on a problem for a very long time if it consists of a very large number of bits. To concretize this, this is where the intersection of quantum computing and its impact on cryptography comes into play. Because the idea is that in order to crack somebody's encryption key, an encryption key is basically a large number of bits. And so it is theoretically possible to decode some piece of encrypted information by literally going through every possible key at a time, right? 0001, 0010, 0011, 0100, and so on and so forth, right? We have designed keys that are big enough with modern crypto systems for use even in everyday applications like banking, that these systems are pretty secure against even the most powerful computers on Earth. The time it takes for a computer to crack one of these keys, a conventional computer, doubles with every single bit that you add. So in other words, if you have 1,000 bits, let's say it takes a week to crack. If you've got 1,001 bits, it takes 2 weeks. If you've got 1,002 bits, it takes 4 weeks. And that scales really quickly. So
yeah, because of the exponential growth of the address space of potential keys that would be the fit for that algorithm.
Exactly. So the deal with quantum computers is that if you could launch all possible realities, Doctor Strange-like, try a different combination of bits in every single reality, one of those realities will have the key that actually unlocks your password and that gets into all your sweet, juicy data. If that universe exists somewhere in that box, then you have a way of solving in constant or at least polynomial time problems that would have taken exponential time to solve with a conventional rig. In quantum mechanics, because a particle can be in a superposition of all possible states until it's observed, you can build a bit out of that particle that is both a 1 and a 0 simultaneously. The more accurate way of describing that is that as long as it is supercooled in this sealed environment within the guts of the quantum computer, you can almost think of the guts of the quantum computer as a sort of universe unto itself that's been separated from our own reality. All possible versions of that little miniature reality exist simultaneously.
And this has all been theoretically true for quite some time. What makes this particular announcement from Google different is that this is being done practically. This idea is verified quantum advantage, which, as I understand it, is the idea that there has been verification that by quantum means, a specific algorithm can be solved or solved for faster than it can be done in a classical computer. That's what makes this moment so interesting to computer scientists.
There have been a lot of false promises about quantum supremacy in the past. It's very difficult to perform an apples-to-apples comparison between how fast does a conventional machine solve something versus how fast does a quantum machine solve something. Like, maybe you don't measure the number of transistors, maybe you measure the wattage or power consumption, right? So this announcement is a really big deal because there is no possible equivalent of conventional machine that can be explained as solving this problem that Google's Willow computer solved. I think it said something like our best supercomputer could do on this problem would be something like 13,000 years or something like that. Is that right?
It's 4 or 5 or more orders of magnitude. It's significant.
Yeah. And this is something that Google Willow solved in like minutes. Yeah. Now, the theoretical explanation is that what happened was, like I said, Google Willow explored all possible realities inside its little quantum box, and in those realities, one contained the answer, and so we just read that one off. It's called a collapse of states. When you have a superposition of many different universes, the act of observation causes a phenomenon called wave collapse, which causes us to basically live in one of those universes.
If you're wondering how it is that we can verify this, I'm guessing, I mean, to get back to your example of encryption earlier, with the premise of encryption, that most of the encryption that we use is that it's much easier and faster to multiply large numbers together than it is to factor them. So you can actually create a problem and then test it very quickly if you have the solution.
These are called one-way problems, and they come up all over the place in math. In computer science, we have this concept called NP-completeness, which is a class of problems that take exponential time to solve, but only polynomial time at best to verify that the solution that you found is in fact the solution.
So let's talk a little bit about the applications of this. In the video that I saw, the press release that came out of Google, they were talking about specifically one use case they talked about was drug discovery. Anything that involves complex mapping of structural shapes was something that they were talking about as being potentially, we're not there yet, but it is interesting, potentially being a dramatic improvement using this new technology.
So you were reading a good article right there, because it's zeroing in on a very esoteric use case, the discovery of shapes of organic molecules. Notice what they're not talking about is, ending all of encryption as we know it and completely derailing the internet. I don't know if the articles that you read said anything about the applications of quantum computing to artificial intelligence, for example. That's definitely something that people are curious about. And this is why I've been reluctant to make this episode. I've known since we started doing this show, sooner or later, I would have to start talking about quantum computing. I've been able to hold off because I've always been able to say, like, okay, well, we haven't achieved quantum supremacy yet. Like, this isn't a really big deal. It's it's a very limited application. And now, with all of the news being abuzz that we have hit quantum supremacy, now I actually have to talk about it. People believe that there's an intersection between artificial intelligence and quantum computing, both good reasons and bad. The good reason is that artificial intelligence, in its current form, with neural networks, take enormous amounts of compute. And everybody knows that. Like, everybody knows these things are expensive to run, even more expensive to train, and though the compute requirement is going down, both with improved hardware and, more importantly, as I keep harping on, with better algorithms, the fact is that if there's some way to parallelize that compute not across, like, layers of an NVIDIA card, but across alternate realities, then it's very clear to a lot of people that, like, somehow that's got to have some impact, right? Now, the less good reason why people believe that there may be some intersection between quantum computing and artificial intelligence is that both have this sort of wooey, vague connection to consciousness in the popular zeitgeist. Artificial intelligence is an electronic embodiment of a mind, and quantum computing has to do with the collapse of alternate realities upon observations by a conscious observer, and that kind of sits on the same throne, so to speak, in a lot of people's minds. Obviously, the underlying reality is not that mystical, but this is why a lot of people sort of who talk about one are very excited about the other.
Well, it sounds very abstruse, right? The idea when you say with a straight face, alternate reality, alternate universes, it's like really hard to get your head around this in a practical way that doesn't have anything to do with science fiction.
Yeah. To put it in layman's terminology, the act of observation by a conscious observer is not realistically acknowledged as having anything to do with, like, any kind of, like, spiritual essence or soul or mind or anything like that. It has to do with the fact that the active observation of a subatomic particle causes a cascade reaction among other particles. You can't observe an electron by itself with your naked eye, right? You need to have it inside of a detector, and then that detector needs to be connected to a screen, and then that screen is showing, let's say, a big up arrow or a big down arrow. So the observation separates the universe in which the electron is up from the one where the electron is down, not because you, the sentient being, observed it, but because the sheer number of atoms that are in different states in the universe in which that monitor is displaying up than the one in which it's displaying down. Basically, when it's just one electron that's pointing up or down, it can do that in isolation of all other particles in the universe. But the moment you put it in a detector, the moment you put it in a machine that will measure it, then that active measurement causes that state of that electron to affect the states of many, many, many more particles. And that's why we talk about it sort of collapsing into one universe or another.
Yeah, and by the way, some of these ideas like Bell's theorem are still controversial even within the physics community.
Very true. Bell's theorem is the thing that proved that this isn't all just philosophy, specifically experimental verification of his theorem. There was a physicist named Bell, I believe in the late 60s, who formulated a measurable distinction between this superposition theory and a competing theory, which was called the hidden variables theory, which is still very popular in a lot of scientific circles for various reasons.
The idea here being that there are hidden local variables that account for the perception of entanglement.
Exactly. Prior to Bell, it was generally assumed that this whole concept of alternate universes or entanglement states, whatever, was purely academic. It was purely just mathematical notations, right? Bell found that this entire set of equations actually does have a real physically measurable impact if it were true. And sure enough, these quantum behaviors are demonstrated in the real world exactly how they appear on paper, which frankly is still tripping a lot of people out, myself included.
I think the other reason why people are interested in the potential intersection of quantum computing and AI is there is this thought that computers being infinitely more powerful, or many, many, many orders of magnitude more powerful than traditional classical computers intersecting with AI technology, the idea that that could become somehow exponentially more powerful by running it on a quantum system. I think that kind of like freaks people out in some ways and also, excites them.
I've got a friend of mine who's created a company, I believe he sold it for a pretty good chunk of change, that has already made quantum resistant routers or quantum resistant VPNs. He has built a company around the idea that when quantum computing becomes mainstream, that all modern encryption technology will basically be rendered obsolete and you will need to have a new VPN paradigm because none of your connections are going to be secure anymore. So people are already very concerned and trying to get prepared for a reality in which quantum supremacy is a regular everyday occurrence. There's a big, big but with all of this discussion, and it has to do with the question that you asked about applications such as finding the shapes of organic molecules. And that has to do with what exactly this Google Willow system actually did and what equation it solved and exactly what task it performed that would take a supercomputer 13,000 years or whatnot. What have you read as far as that goes?
Almost nothing.
So the specific equation that this Willow machine, did I say Whisper again? I meant Willow. So yeah, I kept calling it Google Whispers, and so Ash has punished me by getting Careless Whispers stuck in my head all evening.
Yeah, I sent him the Wham video. That was my big contribution to this video, actually.
Hey, better that than last Christmas.
That's gonna be stuck in my head.
I'm still surviving through Whamageddon, so this season has not yet been ruined. But the point is that this machine solved an equation called quantum echoes, or more appropriately, Loschmidt echoes. This is a very complicated equation that describes the way that small perturbations in a quantum system propagate through time and also through multiple interactions in that system. So in other words, if you've got a bunch of subatomic components and they're all linked to one another in some way, such as all being part of the same organic molecule, then this equation represents the way that a slight perturbation of one of those components will affect other components elsewhere in the system. This is a big, big deal when it comes to understanding how, like, valence orbitals will shape a protein. It also has applications, fittingly enough, in quantum computing. And that's where my big caveat to all of this is going. The way that you would solve this for any given system requires the inputting of the parameters of that system. If you have a particular organic molecule, you have to encode its structure into the parameters of the formula. Basically, you have to fill in the values in the Loschmidt Echo equation. And once you do that, then you can run the equation forward and see what its answers are, right? So it's not a general form solution. It's not the kind of thing where, like, you're trying to take a complex equation and reduce it to a simple equation. It's a matter of, like, I have a specific instance of a system that I want to compute these values for.
Well, here's my big takeaway. It's really, really interesting, but we have to wait and see where this ultimately lands and how this plays out practically.
Hold on, are you wrapping me up? Because I haven't stated the big thing yet.
What's the big thing? Don't save it any longer. Jump out. Tell us.
This is not a general purpose computer. Google Willow is not universally programmable in the Alan Turing sense of the word. So it cannot be used for running your AI faster. It cannot be used for cracking your encryption. It is a machine that can only be used for one specific thing, for the solution of Loschmidt Echo equations for various quantum systems. It's actually even more reductionistic than that. that, it's not a coincidence that the equation that this thing is solving happens to be an equation that predicts the evolution of a quantum system, right? So look at what's really happening here, right? You've got a quantum computer, which is a quantum system that's designed to solve an equation that determines where perturbations in a quantum system will propagate. You run this quantum computer, and running the quantum computer involves, by definition, observing the propagation of perturbations through this quantum system. So at the end of the day, what you're reading is the results of a machine that literally went through the physical phenomena that it is supposed to be computing the equation for. Well, if you ask me, and this might get a lot of pushback. It doesn't seem like it's solving an equation. It seems like it's just doing the thing that the equation describes.
Essentially, what you're saying is that it's a very specific use case taken to highlight all of the advantages of this particular form of technology to solve a very specific type of equation that is essentially ideally suited based on the properties of the technology itself.
It's not that it's even solving the equation. The machine itself is subject to state propagation that is described by the Loschmidt Echo equation. So it solves the equation by simply doing the thing, by simply letting its physical state propagate, and then letting engineers at the end of that propagation measure the state that it has fallen into. Essentially, it's like this. Imagine I've got a much simpler equation. Let's say I've got high school physics and I'm studying Newtonian mechanics, right? And I've got this equation that describes how a projectile will fly if I give it a certain acceleration, right? I can numerically solve that equation, right? I can compute its momentum. I can sit there with a pen and paper and whatever. I could build a computer that solves that equation. It can be a digital computer that does all that number crunching for me. Imagine I said that I built a machine that can solve this equation, and that machine literally just launches a projectile, and then I measure how far that thing fell just by taking a tape measure. And then I can be like, okay, well, this machine is an equation solver for Newtonian mechanics for projectile trajectories. I don't know about you, but I wouldn't call that a machine that solves the equation. I would call it a machine that just does the thing, and then you measure what it just did, you know?
I see your point. It is an interesting question, and it seems as though this world just gets so weird so fast that it's really hard to understand that one material distinction that needs to be made.
It's really controversial. I'm going to get a lot of pushback for this, but it seems to me that like if you what this machine does is you want to compute let's say the shape of an organic molecule. You encode that molecule structure into the relationships of the gates of this quantum computer. It's not exactly a one-to-one relationship, so it's not like there's, for every bond there is a specific gate that describes that bond. It doesn't work like that, but you do set up a physical system whose evolution can be mapped in a physical level to the evolution of the system, this organic molecule. And so what you've got essentially is not so much a computer, but a physical model.
Are the structures of these organic molecules more or less complex than the shape of that ring?
I mean, Google Willow only has 105 bits, and that's qubits. And that's actually something to point out as well, which is that it is a huge engineering challenge to get a 105 qubit system working in this superposition isolation state. An organic molecule, every portion of that molecule takes several bits to represent. Every atom, every valence electron. There is a limit to the complexity of organic molecules that can be represented by Willow specifically.
I went and did some homework on this topic afterwards and found that even something as simple as a carbon dioxide molecule, which is about as simple as you can get as far as organic molecules go, would take hundreds of qubits to fully represent. You might be able to squeeze the valence structure of carbon dioxide into the 105 qubits available to Willow, but it's highly doubtful that you'd be able to represent anything more than that. The specific case study that Google Willow performed was sort of a benchmark test, but they also included a simulation of some NMR spin alignments, which basically are relevant for MRI, that's magnetic resonance imaging technologies. But that too was mostly a benchmark of sorts. They were testing to see whether or not the machine would produce an already known answer. So I think it's reasonable to assume that we're going to need a much, much bigger machine than Google Willow with a lot more than 105 qubits before we start to see this technology being useful for actual real-world medical research and other cutting-edge applications.
If Willow were to scale, if the kind of technology that went into Willow were to scale, it would in fact be capable of representing very, very large molecules indeed, theoretically. But in practice, Google Willow right now would not be able to represent an organic molecule whose complexity is on par with this ring.
Well, Mikhail, I've learned a lot here today, and yet somehow I'm more confused than when I started. It is just a very complex and interesting topic. Listen, we went from EPR to careless whispers. Great conversation talking about this. Final thoughts, key takeaways that you'd like to leave our viewers and our listeners with.
The key takeaway is that quantum computers are still very much specialized machines. They are not yet general purpose computing devices that fall under the rubric of what we would call a computer under Alan Turing's definition of the term. They are still very much on par with machines that we would basically more think of as analog computers of yesteryear. While the achievement of Google Willow is really, really impressive and is valuable for its own sake, and also for the sake of very closely related technological avenues, such as medicine, such as materials science, such as superconductor research, all of which do exhibit quantum properties that can be represented by machines like Google Willow, and for which research will be advanced by the existence of machines like Willow. While quantum computing technology is in fact still valuable for those particular cases, this thing that is making the headlines is not a precursor to general quantum computing technology. This is not a way for us to eventually open the door to machines that can do simultaneously in quadrillions of alternate universes what it takes a single machine to do with iteration in our own over the course of trillions of years. We are not there yet, and this avenue of technology that Willow performs is not directly a path that will get us there.
Shockingly, I think I understood most of that.
Thank you.
Mikhail Voloshin, always a pleasure to do this with you. Hopefully our audience is not in the same state that Phoenix is right now.
Hopefully not, Ash.
Thanks for watching, guys.